abstract reasoning. And I'm going to ask you a really simple question. What do you think about the following? If you take an infinite collection of numbers that are all positive, it's a big pile of positive numbers, and you add them all together. So you're doing an infinite sum. Is it possible that you could have a finite answer? So can you add an infinite number of positive numbers together and get a finite result? So think about it. Think about how could that possibly happen? Can you add an infinite number of positive numbers and get a finite result? I've seen yeses, nos, maybes.
Go watch this Veritasium video.
If you know Veritasium, you know the answer. So the answer is yes. You can, and you've done it probably an uncountable number of times in your life already. When you look at something like you tell me this, what is 0.3 repeating equal to? 1/3, right? I don't think anyone disagrees. Well, 0.3 repeating is 0.3 plus 0.03 plus etc. So here you are adding an infinite collection of positive numbers and getting something finite, the third. So you do it all the time. It's just that we've never talked about it in that way, that you're actually adding up an infinite number of positive numbers and getting a finite answer. So that's an important key to what we're about to talk about. When we are dealing with improper integrals, the concept is similar because we are talking about trying to figure out whether an unbounded area, so an unbounded area is an area that continues on forever. You can't put a circle around it. If you have a region that's bounded, you could put a circle around it. But this area goes on forever, so you can't put a circle around it. We call it unbounded because it goes on. There's no bound. It doesn't end. And the question is, will this area be finite or will this area be infinite? So the first thing we have to understand is that, oh yeah, it could be finite. Because when we think about area, we should be partitioning into a bunch of rectangles. The area of a rectangle is just a positive number. So we should be visualizing an infinite collection of positive area rectangles. And so the question is, well, what is the necessary condition for this infinite sum to be finite? And there's a couple of things. The first thing that is absolutely necessary is that this curve has to go to 0. If you're not adding numbers that are very close to 0 out in the tail of this infinite sum, there's no way the area is finite. So we absolutely have to have that curve approaching 0. It's also going to be the second condition. If we look at something like this, these numbers are going to 0, but we will show later that this sum is actually infinite. So it's not sufficient that the numbers go to 0. It's necessary, but it's not enough. So they not only have to be each individually going to 0, they have to be going to 0 fast. They've got to be going to 0 pretty quickly. So in order for this infinite region here to be finite, I shouldn't call it infinite, because infinite we get a little tangled up in, are we talking about the shape of it? Is it infinite? Or is the value of the area infinite? So we should say this unbounded region, not this infinite region. So this unbounded region, for it to be finite, this curve has to be going to the x-axis, and it has to be going to the x-axis fairly quickly. So those, and then we have to figure out what that means. Well, what does it mean to go to the x-axis quickly? that's basically what the rest of the semester is all about, figuring out when these numbers are getting small fast enough for it to be finite. That's a big, big question. So you've dealt with definite integrals. A definite integral is when you have numeric limits of integration. All right, so if we integrated from a to b, that would be a definite integral. And that's what I'm showing in the dark gray here. And the idea is that we are going to take this improper integral, and we can see that it's improper right away because we see that infinity in the limit of integration position. So if we see an infinity, we know it's an improper integral. And we have a whole new technique for an improper integral. An improper integral is going to be evaluated by taking this definite integral right there. So this is a definite integral. We know that's finite. If you integrate from a to b under a curve, you're going to get whatever the area is. But then to address the fact that this goes on forever to the right, we're going to take the limit of this. This, when we evaluate this right here, you're going to end up with a function of whatever that is. So this b is not a specific number. It's moving. So we're going to end up with a function of b. The a is a fixed number. We're integrating from 1 to infinity or 2 to infinity. So this b will end up getting a function here, and then we're going to take the limit of that function. So here we have an unbounded right tail. Here we have an unbounded left tail. Once again, we can see that this integral is improper because we have this negative infinity right in the limit of integration. So it's jumping out at us that it's not a definite integral. Definite integral would have numbers. So same idea. We're going to build this definite integral right here. There is the definite integral right there. That's going to be a function of b, just like this one. And now, instead of taking the limit as b is going to infinity, we take the limit as a is going to negative infinity. So the concept is that we find a function that represents a definite integral and then take the limit. And if we get a limit that exists, the area is finite. If we get a limit that doesn't exist, the area is infinite. Now, in the case where we have two tails, you're going to be tempted to say, oh, well, can't we turn this into the integral from negative a to a and then just let a go to infinity? And that will not work. It might work in some cases, but not in all. The issue is that if we've got these two unbounded tails, you really have to treat each of them separately. You can't sort of treat them in one fell swoop saying, oh, a is going to go to infinity and let this go from negative a to positive a. That won't work. So we have to break it apart. And it doesn't matter where you break it apart. You can break it apart right at the origin. You can break it apart anywhere. It doesn't matter. Anywhere you break it apart is fine. It creates two improper integrals. And so you just have to do them separately. You have to do a left improper integral and a right improper integral. So for this two-tail area to be finite, both the left tail and the right tail have to be finite. If one of them is infinite, then the whole thing is infinite. There's no way for this side to be infinite and this side to be finite and then the whole thing be finite. If one of them is infinite, the whole thing's infinite. The only way it can be finite is if both are finite. And what we will say, if one of these integrals they either converge or diverge. So if the area is finite, we say the integral converges, and if the area is infinite, the integral will diverge. So 2 new words. Let's try one of these horizontally unbounded regions. So here we're going to integrate from 1 to infinity in this example. And the function I'm going to choose as the first example is 1 over x squared. So 1 over x squared looks kind of like that, as does 1 over x and 1 over x to the 5th and 1 over x to the whatever. So they all sort of look like that ski slope, 1 over a power of x. So we are going to create this definite integral from 1 to b, and then take the limit of it. So the integral from 1 to b of x to the negative 2. Add 1 to the exponent, divide by the new exponent, and we get this as our function of b. So this tells us the area between 1 and b. So if you plug in b equals 1, you would get 0, because you'd have no region beneath the curve. If you plug in b equals 2, if you went from 1 to 2, your area would be negative 1/2 plus 1, so positive 1/2. And as b gets bigger and bigger, you're going to get an area that's closer and closer to 1. Right? If you're out at 100, the area would be 1 minus 100th. Everyone following? So this is telling us that finite area as b gets bigger and bigger. And now we just take the limit of that as b goes to infinity. So as b goes to infinity, 1 over b goes to 0. The denominator is getting infinitely large, so the fractions are getting closer and closer to 0. So that limit is 1. That tells us that the area is 1. So we get this function of b. We take the limit as b goes to infinity. This is the area underneath that curve. So that unbounded region has an area of exactly 1 square unit. That whole unbounded tail. All right. So this is where it starts to get a little weird. And this is where this leads us to the infinite series, which most people find to be the hardest part of Calc 2, is dealing with the infinite series. But this is the concept behind infinite series, that you can have an unbounded region that has a finite area. Okay, now here's an exponential decay function, 2 to the negative x. Certainly it's approaching, it's got that first condition that the tail is approaching, the curve is approaching 0. It's approaching the x-axis. And then the next question is it approaching fast enough? So we saw in the last example that this 1 over x squared does approach the x-axis fast enough. 1 over x squared approaches fast enough. Okay? So in exponential decay, that's going to approach very quickly. Right? Exponential decay is very fast. That's faster than 1 over x squared. Right? When we think about exponential decay, you can see the graph. It approaches the x-axis real fast. So our intuition should be that this will be a finite area, and we can't even see the area anymore. It gets small so fast down here. So our intuition should be that this area in here, we're going from 1 all the way out, that area will be finite. So let's test. So the very first step, anytime we have an improper integral, the very first step is to write down the word limit. That's always the first thing you have to do. So you need to have proper notation here. And whatever letter you want to use, this book will use a b. So b goes to infinity. And now we have a definite integral here. So this is a definite integral. And it's going to be a function of b once we do the integration. And then we'll take the limit of that. All right, so let's integrate this. We're integrating an exponential. And the integral of an exponential, we start out with itself. So the integral of an exponential is itself divided by the derivative of the exponent. The exponent's linear, so that's the reverse chain rule piece. But we also have a modification if we don't have a natural exponential. This is not e to the negative x. So we have a little tweak that we have to do when we have a non-natural exponential, which is what?
You have to do ln of the base.
We also have to divide by ln of the base. So we're going to put an ln of 2 right down there. So if we have a non-natural exponential, we have to modify the denominator there. Okay. So there's our antiderivative. We're going from 1 to b. This is a limit as b goes to infinity. You don't have to write this subscript every single step. I usually don't write it in the intermediate steps. Wait till the very end, and then we'll get back to it. Now we have a choice. We have this constant right here, which we could factor this constant to the front, or you could leave it in as you're sort of evaluating your antiderivative at the upper and lower endpoints and taking the difference. It does not matter. It's whatever is easiest for you. I'll factor out the constant. It's in the denominator. So I'm going to write it like this, just factoring it to the front. It's in front of the limit now. Constants can come through limits. And so the only part of the antiderivative that's left here then is just this numerator part. I'll evaluate it. So that's 2 to the negative b minus 2 to the negative 1. So we're taking the limit of all of that, and I'll put the subscript back in because now I'm going to actually do it. All right, so does everybody get to that point? Does that make sense to everyone? Everyone see all the steps up to there? So as b goes to infinity. Now, when you have negative exponents, let's actually do one more intermediate step just in case you need it. A lot of times evaluating limits is easier when there's no negative exponents. So it's completely fine and encouraged to do this step if you need it. It always seems easier if there's no negative exponents when you're evaluating a limit. So as b is going to infinity, what is this fraction approaching?
0.
0. Everybody agree with that? Numerator is constant. The denominator, 2 to a number that's increasing. That means the denominator is getting bigger and bigger and bigger, so the fractions are getting closer and closer to 0. So the limit of that piece is 0. And what's the limit of this constant?
Just that. So
Itself, right? Yeah, the limit of a constant is itself. And so we end up with negative 1 over natural log of 2 multiplied by negative 1/2. And we end up with 1 divided by 2 natural log of 2. So that is the area of this unbounded tail. So we will say that this integral converges. We'll say that this area is finite. And that is the actual value of the area. All right. Try another one. So this one has a left tail. So we're integrating from negative infinity up to 0, right there. So we're trying to find the area here, figure out if it's finite or infinite. And just looking at the graph, now looking at the graph, of course, is just sort of giving you a clue. It's not definitive. But does it look like that curve is approaching the x-axis quickly? No. In the last one, we saw the curve and the x-axis become indistinguishable very quickly. Right? That's sort of a good intuition for whether it's fast or not. This curve is approaching the x-axis for sure. The limit of this as x goes to infinity, as x goes to negative infinity is 0. So it's definitely, there's an asymptote there. But you can see just visually that it's not approaching it very quickly. But that's not math. That's just giving us some ideas. So we're going to pick a b. We're just imagining b right here, wherever. And we're going to create the definite integral that finds this area. That will be a function of b. And then we're going to let b go to negative infinity and see if we get a finite answer or an infinite answer. So first word we always write with an improper integral. We know it's improper instantly because we see a negative infinity. So right away we know that we have to write a limit. And when the limit is to the left, they use an a in this book, so I'll use an a. And so then we're going to have a limit of an integral from a to 0. And we're going to rewrite this with a negative exponent because it's a lot easier to do the power rule when you've written it this way. Any questions before we do the integration? Integration will be power rule plus a reverse chain rule. So we're going to add 1 to the exponent. So we add 3 over 3, we'll get a 2 over 3. We have to divide by 2 over 3, which means multiply by 3 over 2. So that's the power rule part. And then the RCR part, the derivative of the inside is -1. So we'll divide by -1, which we can just put in front of this thing here. And then we have our limits of integration, a up to 0. Once again, we have this constant that we can pull all the way to the front. Cleaning up what you're taking the limit of often helps. This will be the limit as a goes to negative infinity. So first we're going to plug in 0. And we get 2 to the 2/3 minus. Now we're plugging in a right there. So we're going to have the quantity 2 minus a raised to the 2/3. Then we have to evaluate that limit. So the limit, the first term is a constant. Limit of a constant is itself. So 2 to the 2/3 is just a number. Limit of it is itself. So we're there. And now let's think about this second part. And I find it helpful to start on the inside and to kind of, just sort of build your way out one step at a time. So if a is going to negative infinity, then we have 2 minus infinity. So if a is going to negative infinity, where is 2 minus a going to? Positive infinity. So inside there, this part down here, the base is going to positive infinity. Okay? And then we ask ourselves, what happens when we take this base that's going towards positive infinity and we raise it to the 2/3 power? Where would all of this approach? Infinity also, because in your mind, what you should be picturing, if you have x to the 2/3, you should be picturing the bird wing. Right? It's going, whatever that, if you have a proper fraction as an exponent on x, x to the half, x to the 2/3, x to the 4/5, x to the 9/10, x to the 99 over 200, they all look like a bird wing, if that's a fractional exponent. truly fractional, proper fraction, less than 1 in value. So it all looks like that. So it all goes to infinity, right? No matter what that, if we just sort of look out here, it all is going to look like that. So now we have positive number minus infinity, which the whole thing in here will go to what then? Positive number minus something going to infinity, negative infinity. So that whole thing is going to go to negative infinity, and it's kind of tricky to write this. I'm going to write it this way. Let's write it this way. So it's not correct to write things like this. Like, it's very tempting to say, oh, it's going to be negative. You're tempted to write that, but that's not really. We don't really write infinity and use it like a number, even though it's very tempting. Here we can sort of think about it like it's a number, but it's not. And so when I do this, I'm not sort of treating it algebraically like a number. So what we want to write is just this. So it's going to be positive infinity down here, because this is positive infinity, and if we do this kind of thing, that's negative infinity. Negative 3/2 times negative infinity is that. So we technically don't want to be writing infinity as an algebraic expression, but you can think of it that way. And so therefore, the area is infinite. Therefore, the integral diverges. So these are interpretations of what this means. So if we end up with a limit that does not exist, let's make sure that's clear too. When you have, a limit either exists or it doesn't exist. There's only two choices. If the limit exists, you say the integral converges. When a limit doesn't exist, there's a couple of ways in which it doesn't exist. So let's just go back for 1 second. If we have something like this, the limit let me think before I write down a good example. So I want to distinguish between a limit that all you can say about it is that it doesn't exist versus it goes to infinity. Like, those are two different things, but there's a lot of similarity. So for example, if we have the limit of sine x as x goes to infinity, this limit does not exist because that function oscillates, right? So it's oscillating around. So it's for a limit to exist, the values have to approach a single number. There has to be, it's like a horizontal asymptote. Does not exist. Whereas if you have something like this, the limit of, let's just say x, keep it real simple, as x goes to infinity, it is correct to say this, that it does not exist. That is correct. That limit does not exist. Because for a limit to exist, the function approaches a single number. This is not approaching a single number. It's going towards infinity. But more precisely, you can write that the limit of x as x goes to infinity, you can write that that is infinite. Sometimes when a limit doesn't exist, you can describe how it doesn't exist. So this limit does not exist because the values are getting infinitely large, or getting arbitrarily large. So this one we can't, this is not going towards infinity, right? It's just oscillating, so all we can say is the limit doesn't exist. It's not approaching a number. Here we can describe how it's not approaching a number. It's not approaching a number because the values are getting arbitrarily large. So, but both of these limits do not exist. It's just that this one we can be more precise. So here the limit does not exist, but we can be more precise. The values are the area as we go further and further out is getting bigger and bigger and bigger. It's going towards infinity. So we can describe it a little bit more precisely than just D and E. Okay. Let me just remind myself. Okay, let me do one more and then I'll let you do one.
What was the divergence part?
So if
That's as if it goes to infinity?
just like a limit either exists or does not exist, an integral either converges or diverges. So an integral converges if the area beneath the curve is finite, and the integral diverges if the area beneath the curve is infinite. So converge, diverge are the two options for an integral, and exist and does not exist are the two options for a limit. So here we have that double tail situation. We have an improper left tail, we have an improper right tail. We can't treat it as one integral. We've got to break it apart. Obviously, 0 is a great place to break it apart because then we have a limit of integration that's 0, which always makes our life easier. We do not have to. We could break this apart at -1 where it appears to be symmetric. We could break it apart at positive, wherever. It does not matter where you break it apart. So if it does not matter where you break it apart, choose 0. Because the limit of integration that's 0 is almost always beneficial. So we're going to rewrite this as the integral from -infinity to a dx divided by that polynomial. Oh, and I'm going to make it 0, though. I'm choosing 0. Choosing 0. Plus the integral from 0 to positive infinity of the same exact thing. So we have that. So now we have two improper integrals, a left one and a right one. So we're imagining breaking this apart right there. And on this side, we're picking an A that's going to give us a definite integral there, and then we're going to let A go towards -infinity. And on the other side, we're picking a B to get this area, and then we're going to let B go to positive infinity. So we have first word that we always write as we start to evaluate an improper integral, limit. So this one's going to be the limit as A goes to -infinity. We're going A to 0. This denominator is a quadratic that is not factorable. If it was factorable, we could use PFD. But it's not factorable, so we complete the square, and we're going to rewrite it as x squared plus 2x. We need a 1 to complete the square. So we're going to take a 1 away from that 5 and write it this way. Plus the limit as B goes to infinity from 0 to B, and the same exact integrand. So we have that. So there's our translation. We've identified both of these as improper. We see the -infinity and the infinity. We know they're improper. So the next word we write down in the evaluation is limit. And that will put us right there. All right. So now we have to evaluate these two integrals. So the easiest thing to do first is complete the square. So we're going to have x plus 1 quantity squared plus 4. And the second integral is going to look really similar. And hopefully you're recognizing this as being in arctangent form. Both of those are arctan form. But what we'll do is factor out the 4. The denominator is the sum of squares. It's easier if we have a sum of squares with a 1. So I'll factor out that 4, and we can factor it out of both integrals simultaneously. We can put a big set of brackets and rewrite this as follows. And when we factor out that 4, we are imagining this denominator. It doesn't have a 4, so we're imagining a denominator down here of 4 by putting a 4 up there, so that when you factor out the 4, you're left with what I have there. And then in the second position, we're going to have something very, very similar. So now, both integrals are written with the sum of squares in the denominator with a 1. Now we can integrate directly to arctangent. And somebody tell me what the derivative of that quantity is, because we'll have to know that. What's the derivative of that?
1 over a. So 1 over 2.
1 over 2, yep. So if we had to write this out, if it's not completely obvious what the derivative is, if you expand it and do your distribution, you see that the derivative is, this is linear, so the derivative is the slope of that line, it's m, it's the coefficient of x. All right, so that allows us to do reverse chain roll. So reverse chain roll will come into play right here. So this will be arctangent of x plus 1 divided by 2. So it's arctangent of whatever's in parentheses. But then the reverse chain rule says now divide by the derivative of what's inside. So dividing by 1/2 means multiplying by 2. So we'll have that from a to 0 plus limit. Again, we're going to divide by 1/2 multiply by 2, and it's the arctangent, again, of the same quantity. And then close the brackets. Oh, and we have to do our evaluation symbol, and then close the bracket. All right, we're getting close. So we still don't even need the subscript of the limit yet. We'll get back to it eventually. So in here, we're going to plug in 0, plug in a, and take the difference. If you wanted to, you could factor this 2 to the front of the limit. If that is easier for you to factor it or just leave it, does not matter. Just remember that it's going to be, if you don't factor it out, it's part of both of those. It's part of the 0 and the a. So if we leave it in, we would have 2 arctangent of 1/2 minus 2 arctangent of a plus 1 over 2. Now the second part, we have limit. Let's just leave the 2 in again. So we're going to have 2 arctangent b plus 1 over 2 minus 2 arctangent of 1/2. I'll put the subscripts into the limit now because we're going to evaluate. So the one on the left is to negative infinity, the one on the right is to infinity. So this is the limit as a goes to negative infinity. This is the limit as b goes to positive infinity. So now we have to remember the graph of inverse tangent. So inverse tangent is this interesting graph that has two horizontal asymptotes. Very few functions have two horizontal asymptotes. So this is y equals pi over 2 right there. And this is y equals negative pi over 2. And the graph of y equals inverse tangent. So when we look down here, the first part's a constant. We don't know what it is, but we know it's a constant. 2 inverse tangent 1/2, some constant, it's a number. So the limit of a number is a number, self. This is the part that we have to think about the graph. Bless you. So inside here, if a is going to negative infinity, and you add 1, the numerator is still going to negative infinity, and if you divide by 2, this is still going to negative infinity. And so we are saying, what does this function approach as the inside goes to negative infinity? Well, if we look at arctangent, as the inside goes to negative infinity, what does arctangent approach? Negative pi over 2. So this piece right here approaches negative pi divided by 2. Now we look over here. Same thing with the first term. That's no. Same thing with the second term. It's constant. So that the limit of itself. Limit of a constant is itself. This part. So in here, as b goes to positive infinity, if you add 1, that's still going to positive infinity. And if you divide that by 2, this whole quantity in here is still going towards positive infinity. And now we ask ourselves, well, what about inverse tangent of that? So we look at our inverse tangent function, or we visualize it as the inside of inverse tangent is going towards positive infinity. The inverse tangent function is approaching pi over 2. So that is going to approach pi over 2. And we are at this stage then. So we just took the limit. So we've got the 2 inverse tangent of 1/2 minus negative pi over 2 plus, this part goes to pi over 2. There's a 2 in here that I dropped. So this part right here is going to negative pi over 2 multiplied by 2. There should be a multiplication of 2 right in front of it. And then here, same thing. We've got the 2 in front, and then this function part goes to pi over 2 minus, this is a constant, limit of a constant is itself. All right, I see some cancellation. So 2 arctan 1/2 minus 2 arctan 1/2, so this will cancel with that. We will be left with positive 1/4 out in front, multiplied by this part here is just going to become pi. The 2's are going to cancel with each other here. Let's use that. So those are going to cancel, those are going to cancel. So here we end up with plus pi. Here we end up with plus pi. And that's gone. we end up with pi divided by 2. That'll be the area beneath that bell curve. All right, so questions on any stage of this beast? Some of you have had stats and seen bell curves before. Some of you probably haven't. And so a lot of times what they'll do in statistics is create this bell curve where it's centered at the origin, and they create a function that does that graph, which has area of 1 underneath that whole bell curve. So you get that whole probability thing going, where 1 is the full area. And so the function that they use to do that will be an exponential function with a natural base. They fiddle with the exponent to force the area to be 1. Whereas the curve that we picked up here has an area of pi over 2. But you can imagine modifying the function so that you create an area of 1. All right, any step there you have a question on? Any part of the limit evaluation? All right, I guess you're ready to try one. Let's go. All right, so let's go with this one. So try this one on the top right. Or that's the left, isn't it? Top left. Try that one. Let me know if you need a nudge. Yeah.
Isn't this just inverse tangent times inverse tangent? Or am I crazy?
Well, it's a substitution.
Okay.
So if you let u equal inverse tangent, its derivative is present.
Right.
So you can use u substitution.
Got it.
So yeah, u substitution will be the order of the day. Did I just give it away? No. You already did.
Choose on someone else.
You were on, you were doing it a different way. I can't wait to see that.
Oh,
Now, whenever we use u sub is viable if what you think about picking for u has a derivative that's in the integrand. And so u substitution here is going to work perfectly because the derivative of arctan is in the integrand.
I decided to just integrate at the top. The thing is, you could just do that. So what do you do? I just.
What's your intuition? Is your intuition that this should be a finite area or an infinite area?
16 times 2.
So if you just look at the graph is a clue that it should be finite. That you can just sort of tell that the graph becomes indistinguishable from the x-axis fairly quickly. Another thing that is a clue is that we already integrated 1 over x squared. Right? We integrated 1 over x squared as our first example, and we showed that that was a finite, unbounded right tail. And if you look at this, it's very similar to integrating 1 over x squared. The numerator is a bounded function. So if the numerator is a bounded, it's not a constant, but it's like a constant. It's never any bigger than pi over 2, right? So the numerator kind of acts like a constant, and if we have an integral that's finite, and you multiply it by a constant, it's still finite. So that would be another way to sort of intuitively realize that this should be finite.
So one thing I've never understood is if it's never actually getting to 0 and it is going through an infinite amount of x, how is it that it's a finite area? Because by the nature of infinity, it's still, if we can guarantee that there's always numbers being added, would that not be an infinite area?
So the best example that will convince you is looking at that, like looking at something like this. 0.9 is positive, 0.09 is positive, 0.09 is positive. But you know, what is this
No
sign?
matter what number it is, you are theoretically adding an infinite number positive.
Which is 1,
Because in between every number is
right? That you're adding.
Yeah.
These are all positive.
It's not.
They're just getting close to 0 super fast. And so it's that is the argument that should convince you that it's possible.
And then you
Right?
get
That's it.
I mean, I get that that's analysis.
Exactly. Out in the tail, you're adding
In theory,
something
though,
insignificant.
in theory, though, it's so situated.
No, it does. It makes perfect sense.
There's still always going to be, it's never going to
So,
actually get to 1.
if your salary is $1 million and someone's adding pennies to your bank account for the rest of your life, do those pennies matter?
I mean,
No.
how many
If you had a
pennies?
penny, yeah, I mean, if you had 1 penny every day for the rest of your life and your account's already worth like $5 million.
No, I get it. It's just that it's like,
Yeah, I mean, that's the math, right? That it's a little, it has this weird whack-a-mole feel to it.
How are numbers?
yeah.
Okay, so let's go ahead and do this using U sub. And again, U sub is a great candidate because if we let U be inverse tangent, the derivative of inverse tangent is present in the integral. So we'll have du is 1 over 1 plus x squared times dx. And that's inside the integral. So first step, I'm going to write down limit as b goes to infinity. And this will be 1 to b of that. So first step, we always write down the, oops, I changed the order. It does not matter. We know how to commute. So now we're going to notice that the derivative is present right there. So this integral will become the limit of, that's u, and that's du. All right, u du. Now these limits are different. We would have to plug in these x limits down here. This is one of those situations where it's just easier to go back to the original limits. Just put some placeholder limits in for a moment. Especially when you're dealing with evaluating an inverse trig function. Probably better just to put it off. So this antiderivative is u squared over 2 with our placeholder limits. And then we're going to convert. I'll factor out the 1/2. U is arctangent, so we have arctangent of x. Now we're back to our x limits, which are 1 and b, and this limit is as b goes to infinity.
It's arctangent of x squared.
arctangent of x, quantity squared. Thank you. So the 1/2 came out. U is arctangent. Everyone saw that. Good. It worked. Okay, so let's go ahead and plug in our upper and lower limits of integration and see what we get. So limit as b goes to infinity. We're going to have arctangent of b, quantity squared, minus arctangent of 1, quantity squared. So we're taking the limit of all of that. Arctangent of b. So b is going to infinity, and remember that the limit symbol distributes. So we're going to take the limit of this minus the limit of that, and the limit can come inside the square. Right? The squaring function is a continuous function, which means the limit can go to the very inside of it. Just like when you take the limit of a square root, we took the limit and put it inside the square root, and that's because the square root is a continuous function. And the limit symbol can pass through continuous functions to the inside. So the limit of this whole quantity as b goes to infinity, we go to the inside. Arctangent as b goes to infinity is pi over 2 again. So we are going to have pi over 2 squared minus, this is constant. So the limit of a constant is itself, so we don't have to deal with any thinking of the graph or anything. Arctangent of 1, that's a constant that we know. Arctan of 1 is the angle in quadrant 1 that has
pi over 4.
pi over 4, has a tangent value of 1, which is pi over 4. So this is going to be pi over 4, quantity squared. So that's where we're at. So we will have 1/2. That's going to be pi squared over 4 minus pi squared over 16. Multiply this one by 4 over 4. So that's going to give us 4 pi squared minus 1 pi squared. That's 3 pi squared in the top. And in the bottom, we have a 16, but we double it, so we get a 32. That'll be our area. So let's think about the big picture for a second. We ended up with an integral that we could evaluate it, so the integral converges. And this value that the integral converges represents this unbounded area. So this unbounded area, this area that goes on forever, is actually finite. Finite area. And we want to try to get the distinction between infinite and unbounded. Make sure when we think of unbounded, we're thinking of a region that goes on forever and ever. Walter?
I'm just curious, just because of the way we've been talking about this, we're finding the area of the trailing end. Does that also include the area of the rest of the integral, or is it just the trailing end?
So it's from this moment
Okay.
all the way to the right. So this everything in here that's underneath the curve. So everything that we traditionally think of between the curve and the x-axis. So it's all that area.
It's the full area.
Yeah. So the blue part is representing, so we sort of scaffold our way through. We say, okay, well, let's find the area of this, because this is definite, this blue, that's a definite integral. But when you put the b in there, you're ending up with a function. And then we let that value go to infinity. So we get a function of b, we let that b value go to infinity, and it's kind of a sneaky way to get at it. We first create this as a function, and then we let b go to infinity to get the total value.
When it's finite, will it always be like a forever trailing decimal?
So, no. We had one earlier that was 1, didn't we?
Oh, okay.
Right? I think the very first example we had, that area was a positive integer. So it was not an irrational number. It feels like, oh yeah, this is super weird. If it's finite, it's probably an irrational number, but it's not always. Yeah, we saw at least one that had a integer value. Yeah. Okay, let's take our 10-minute break, and then we'll do some more improper integration. Right, we're getting wild. Improper integration. We're getting out there. Like proper integration was hard enough. Now we're doing improper integration. No.
And I can't like square these notes here instead.
No.
Okay.
No. So, great question. So when we have inverse tangent of, I'll put a B here. So this squared, there's no other shortcut to write that. This means inverse tangent of B multiplied by inverse tangent of B. So that's the only way to interpret it. It's kind of, as soon as we put an inverse symbol here, we don't have any shortcut notations. Like it is true, if you did this, we do have a short abbreviated notation, and you could write that like that. But as soon as this is the inverse function, you can't do that.
Okay.
Unless you use a different notation for the inverse that doesn't have this -1. So that -1, you could write it as arctangent,
Yeah.
like they did in the old days. If you wrote it that way, then you could do that. No book out there ever does this, we always use this -1 notation these days. But if you did happen to use that notation, you technically could do that.
So it's whatever the angle is squared.
Correct.
That's the only thing. Okay.
Right. So this in here is an angle, and you figure out what that angle is first, and then you square it. Yes. And yeah, it's super tempting to want to try that.
Yeah.
Because we talk about laws of exponents all the time. We're always multiplying those things. But as soon as we have this notation for inverse, we can't do that. Because this is not really it's not an exponent. That is not an
It's like
exponent.
not actually a number, it's just something.
Yeah, it means this. And in math, unfortunately, we use the same notation for many things. Like you think about intervals and points. It's like if you just write 2, 4,
Oh, sure.
do you mean the interval? Do you mean the ordered pair? Like, there's, you have to have context. And so whenever we have that -1, the context isn't, oh, that means inverse. It doesn't mean exponent, even though it's in the exponent position.
Yeah, like it could be cotangent, but it's not.
It could be, but it's not. It's not reciprocal.
Yeah.
So the question then is, sometimes inverses are reciprocals. Like when you think about multiplication, do you know what the multiplicative inverse of 3 is?
I'm guessing 1/3.
Yes, that is the multiplicative inverse. So 2 numbers are multiplicative inverses if they multiply to 1.
Okay.
And that is true. 1/3 and 3 to the negative. So this is an example where the inverse and the reciprocal are the same. So for multiplication in the number system, the reciprocal and the inverse are the same, the multiplicative inverse. But the function inverse is totally different.
Like this isn't the same over 1/tangent.
Yeah, this is not 1/tangent.
Okay.
Because for functions, the inverse of a function is not a reciprocal. It's like natural log and e to the x are inverses of each other, but they're not reciprocals of each other. Right? The inverse of e to the x is natural log of x. And that means that if you put the natural log into the exponential, you get 1. Or if you put the exponential into the log, you get 1. So function inverses have a composition nature that gives you 1, whereas multiplicative inverses give you a multiplication that's 1. But function inverses have a composition that's 1.
Yeah, I did.
So you can't
That's what happened.
turn that into cotangent or tangent to the -2, even though it's so dang tempting.
Yeah.
Man, that one I really,
But a lot of times we don't talk, it's not sort of explicitly talked about a lot because it's very rare in calculus, one, to ever get an inverse function that you're squaring or doing something with. So you don't, so it's one of those things that you have to sort of piece together as we go along in math. Oh, wait, that's not the same thing as 1 over tangent. Breakfast of Champions.
A muffin.
Yeah.
Man, that was it. That one had the number, but it's also unlike that.
But within that.
All right, let's go ahead and do our next one. And this one is going to be one of those quantum leap. This is going to be one of those ones that's going to stick with us for the semester. This is going to be kind of what I call the threshold case. So the place that we're at right now is that we've seen 1 over x squared has finite area in that right tail. 1 over x squared was our first example. And we're going to be looking at these situations where we have powers of x in the denominator. So 1 over x is the simplest exponent on there, right? Exponent is 1. And it's going to be very helpful to figure out whether this one converges or not. Now, when we look at the graph, it's definitely approaching the x-axis, going to 0, but it's approaching slower than 1 over x squared. All right, so 1 over x is coming down. 1 over x squared is steeper, and it's going to hit the x-axis faster. As the power of x gets bigger and bigger, 1 over x to the 4th is going to be even faster to the x-axis. Right, the 1 over x to the 4th would go to 0 much quicker than just 1 over x. And so we've seen that 1 over x squared has finite area. So 1 over x squared goes to the x-axis fast enough. So if it goes to the x-axis faster than 1 over x squared, it definitely is going to have a convergent tail. But this is going to the x-axis slower. So we've got to figure out this one. So let's first do our magic and imagine a b right here. And if we integrate from 1 to b, we're calculating this area. And we're going to find a function that's going to represent that area as a function of b. So we're going to rewrite our integral. As soon as we see that infinity, we need to rewrite with a limit. So that's always the first step. So we're going to integrate 1 to b and 1 over x. So this part right here, this is now a definite integral. Definite integral. And it's a function of b. So it will be a function of b in here. That is the key, that we're creating a function of b. Let me just point out one thing off to the side. Is it clear to you that if we have something like this, we call that x in there a dummy variable? Because this is, when we talk about a variable, we mean there's a function, right? There's something that's changing. This is not a function. This is a constant. It just has this dummy variable that's temporary, right? When we do this integration, that variable goes away. This is a constant. This is not a function because its value is 1/3. Right? That variable is just sort of dummy. It's temporary. It gives us a pattern in order to figure out what this number is. Whereas if you integrated x squared from 0 to a, this is now a function. Because when you go and do the integration and you plug in your limits of integration, you get that, and that's a function, right? There's an unknown in it. We don't know what this value, it doesn't have a particular value, it's a function. Depends on what you plug in for A. So that's a function, this is a constant. So we want to just make sure that we're making that distinction, that when we look right here, this is a function. It's not a function of x, it's a function of b. It's a function of whatever that upper limit is. Because the x is going to vanish no matter what. It's a dummy. It goes away. So when we do this integration here, we get natural log absolute value of x, and then our limits of integration. And we end up with limit of the quantity natural log of b. We can take away the absolute value bars because we know that our interval is from 1 to infinity. Everything is positive. Minus natural log of 1. And natural log of 1 is 0. So we end up with the limit of natural log of b. So let's just look at the graph for a second of natural log function. And the natural log function we know has this graph, like that. Passes through 1. Natural log of 1 is 0. And now we're evaluating this limit. We were saying, okay, well, as the argument or the inside of natural log goes towards infinity, where does the natural log function go? To infinity. It grows really, really slowly, but it still is going to infinity. It never flattens out. It's always going up. So that limit of natural log of b is infinity. So this limit does not exist. Even though we say the limit is infinity, that's really bad English mathematically, because that makes it sound like the limit exists and it's equal to infinity. So when we say the limit is infinity, we really mean the limit doesn't exist, and the way it doesn't exist is that the values are approaching infinity. So this limit does not exist. It's just that we can describe how it doesn't exist. So when we say the limit is infinity, that's a little bit of a misnomer, because it makes you feel like the limit exists, but it doesn't exist. Okay, so that means we can say a couple of things. We can say that the area beneath this curve is infinite. We can say this integral diverges. So those all mean the same thing. The area beneath the curve is infinite. The integral diverges. The limit does not exist. The limit's equal to infinity. So all kind of the same thing. All right, so let's go to Gabriel's horn. That's a pretty cool graph. Was not easy to create. Okay. So I don't know if you guys have used the graphing Desmos. Do they call it graphing or geometric? They call it the geometric Desmos. You can put arrowheads and things in there and make graphs that are a little bit cooler than just the standard Desmos graphing. The geometry tool is pretty cool because you can use vectors. So that's what I created all these images in, with those graphs and the colored things, all with the geometry Desmos, which is kind of cool. Okay, so Gabriel's horn. Let's go. Take the curve 1 over x from 1 to infinity. We just looked at it. 1 over x from 1 to infinity. Then we're going to rotate it around the x-axis. That's what we're going to refer to as Gabriel's horn. So this horn goes on forever. We are going to show 2 things. We're going to show that Gabriel's horn has finite volume. All right, so we want to find the volume of that horn. This is the first time we have found an unbounded volume. All right, that volume is going on forever. So we want to show that that volume is finite. So here's what we're going to do. We are going to use the disk method. Shocker. So if we imagine that as the radius of our disk, right there, the area of a disk is pi times the radius squared. So we're going to get a cross-sectional area. Cross-sectional area is a disk. Pi r squared. There we go. Pi. The function is 1 over x, so pi r squared. And we're going to go out to infinity. This is an improper integral. We see that infinity. A little bell goes off in our head. The next thing we write down is limit. We're going to rewrite this function here so that we can integrate it easily. And then the integration, we add 1 to the exponent divided by the new exponent. That gives us this. Plug in the b, we get negative pi over b. Plug in the 1, we get pi over 1, which is pi, and it's minus a minus when we do the lower limit, so we get that. And of course, pi over b as b goes to infinity is going to 0. The numerator is constant, denominator is exploding, so the fractions are squishing to 0. So that shows us that this horn has a volume of pi cubic units, whatever the units might be. So that has an irrational volume, pi cubic units. Now, let's show that the surface area is infinite. So the volume is finite, but the surface area is going to be infinite. All right, so surface area formula, remember surface area. Surface area, we use the circumference, 2 pi r. So if we imagine a point up here on Gabriel's horn, there's a point, and we rotate it around, that's creating the circumference, 2 pi r. So 2 pi r, when we integrate the circumference with respect to the curve, with respect to s, we're going along the curve. Once again, we talked about this a while back. We don't know anything about s values, though. We don't have a tape measure on the curve measuring along the curve. We don't know those s's. S measures on the curve. So we have to do our conversion over to dx. And we remember that ds is the arc length integral. So ds becomes the square root of 1 plus y prime squared. Our function is 1 over x. The derivative is negative 1 over x squared. And if we square the derivative, we have 1 over x to the 4th. So 1 plus 1 over x to the 4th. And r is the function again. 1 over r, 1 over x. So now we have, this is representing the surface area. Improper integration, next thing we write down is limit. Just wrote it as 2 pi over x, just consolidated a little bit. This integral, we can't integrate that. We don't have a technique that will work. The u substitution, if we try it, will not match this x down here. The derivative of 1 divided by x to the 4th is not 1 over x. So u sub is not going to work. But there is a clever concept here, which I would not put this on an exam, but you should be able to understand the concept of it. Do you agree that this part right here is always bigger than 1 if the x's are positive? I guess even if the x's are negative, but x's are positive. That square root piece always bigger than 1, right? Because no matter how big x is, this is still a positive number being added to 1, so the inside of the root is always more than 1, which means the square root of the number is always more than 1. All right. So now, if I take that away, this quantity here is going to be bigger than the quantity without that square root. Do you agree? If I take away a piece that's larger than 1, I'm going to shrink. What's left is going to be smaller. Do you agree? Like if you have 2 times x, and that number, that right there is bigger than 1, right? So is that a good way to describe it? I guess that'll work. Yeah, that'll work. So do you agree that this coefficient is bigger than 1? If I take it away, I'll be left with something smaller, right? If I have 2 times x and I take away the 2, I'm shrinking what's left. What's left is going to be smaller than what we started with. If this is bigger than 1 and you take it away, then what's left is smaller. That make sense? So I think this is a good example here. This is a number that's bigger than 1, and just imagine x is positive. This number is bigger than 1. If I take that away, what's left is going to be smaller than what we started with. Okay. All right. So, taking away this piece that's always bigger than 1, we're left with something smaller than what we started with here. That limit we can evaluate. We just did it a minute ago. The integral of 1 over x from 1 to infinity, we did the 1 to b, right? We got natural log, we plugged it in, and we just showed a minute ago that this is infinite right here. This integral is infinite, which means this integral is infinite, which means the surface area is infinite. So, Gabriel's paradox. We've got finite volume, infinite surface area. If we have finite volume, you can fill it with paint. Right? So if it's finite volume, you can go to the store and buy pi cubic units of paint and fill it with paint. But if it's got infinite surface area, you can't paint the surface. But if you just filled it with paint, you painted the surface because the surface is paper thin. So if it's filled with paint, the surface is painted. So that's Gabriel's paradox, which we will talk about on Thursday. You can think about how you resolve the paradox. How do you resolve the paradox? Think about that, and we can talk about it for a minute on Thursday. But they refer to that as Gabriel's paradox because when we live in this 3D world and we have finite volume, we know that we can fill it with paint. We can fill it with whatever we want. But if someone says, hey, go paint this infinite surface, can't do it. We've all painted bedrooms, and we know that that paint runs out real fast. So we have to think about how we can resolve that paradox. So think about that. It's one of these mathematical things that it's like mental gymnastics. Okay. So let's do another volume. So find the volume of the solid generated by revolving this function, a curve that you would never have to graph by hand. You should be able to graph logs, exponentials, polynomials. Not that thing. I will give you that thing. 0 to infinity. When you look at that, do you think the volume could possibly be finite?
No.
Certainly does not look that way. That curve does not go to the x-axis fast enough. Right? So let's see. Okay, so we're going to rotate around the x-axis. So this distance right here is our radius. And we know that the area of a disk is pi times the radius squared. The radius is the function. So this function gets squared. If we want to simplify this, we could write this as pi multiplied by square root of x squared is just x. Down here we have x squared plus 1 to the 1/3 power. So we're going to have x squared plus 1 to the 2/3 power. So there is the area of the disk at a random x. So this vertical element's at a random x, and when that rotates around, that's going to be the area of that corresponding disk. So if x was 4, we could plug in a 4 right there, and this would give us the area of that disk at 4. So this is the area function for any x value that you plug in. If you plug in 0, you'd get a disk with area 0 because the curve is touching the x-axis right there. So there's not really a disk. It's a degenerate disk. Okay, we now have area. We know to get volume, you integrate area. So the volume will be the integral. We're going from 0 to infinity. We're going to integrate that. Let's pull the pi out to the front. So we've got that. So that represents the volume. Any questions on finding the area of the disk or setting up the volume integral? We see the infinity. We know it's improper. The next word that we write is limit. And for these right-tailed things, they always use b. So limit as b goes to infinity. The pi, we could factor it all the way out to the front, which we will eventually. So this will be 0 to b. And this integral we can evaluate using what technique? U sub. We generally are going to let u be whatever is in parentheses. Oh, there's an x squared plus 1 in parentheses. And what we notice is that the derivative is present. Or the multiple of a derivative. The multiple of the derivative. All right, if we divide both sides of this by 2, we'd have du over 2 equals x dx. So there is the derivative, or a multiple of the derivative. Constant multiples don't really matter. You can always factor. So u sub is going to work really nicely here. Here I'm going to use placeholder limits. It's going to be easier to go back to x. So we have 1 over u to the 2/3. So that was u. So u to the 2/3. X dx is going to be du divided by 2. The division by 2 we can put out in front. So that's pretty straightforward. We're going to factor the pi over 2 to the front of the limit. We're going to rewrite this integrand so that we can use the power rule for integration. We pop that up to the numerator, make the exponent negative. Now we can use the power rule for integration. So we get pi halves, the limit, u to the 3rd, divide by 1/3. And then we have placeholder limits. And then we go back to x. And then we'll use the x limits of integration. So the 3 can come out to the front also, so we'll have 3 pi divided by 2. And then we haven't evaluated the limit yet. The limit is as b goes to infinity. Put that back in now that we're about to evaluate. U, x squared plus 1. So we have x squared plus 1 raised to the 1/3 power. And this was 0 to b. All right, anything at that up to that point? Everyone okay with that? Everyone getting really comfortable with u sub? So then this is going to be limit as b goes to infinity. That's a terrible infinity, a terrible arrow. So plug in the b. We're going to have b squared plus 1 to the 1/3 power. So just plugging in the b right there. Minus Plugging in the 0, we're going to have 0 plus 1, which is 1 to the 1/3 power of all that. So in here, b is going to infinity, which means that part in there is going to infinity. And then if we expand out one more step and hit that 1/3 power, we have a quantity that's going to infinity, and then we take the third root of it. Third root's the bird wing. That's also going to go to infinity. So that part's going to infinity. 1 to the 1/3 is just the constant 1. So if we have a quantity that's going to infinity and we subtract off 1, what's still happening? Still going to infinity. And then if we multiply by a constant, still going to infinity. So this is going to positive infinity. You don't need to put the plus, but sometimes we do it anyway. So that tells us that the volume is infinite. The integral diverges. This limit does not exist. So all those things are how we would interpret that result. All right, any questions on that? No questions? Then let's go on. Doing calculus for 2 hours and 15 minutes is a lot of calculus. I don't know if you've noticed or not. But. All right, so now that we have talked about these unbounded regions horizontally, so those generally arise when you have a horizontal asymptote. Like everything's been approaching the x-axis. Now we're going to turn our heads 90 degrees and talk about vertically unbounded regions. So look at this beautiful picture created in Desmos geometry. We've got a vertical asymptote. We're trying to find the area beneath this curve from A to B. First thing I want you to notice is that it's not obvious that this is an improper integral. Right? You do not see infinity in one of the limits of integration. When we have horizontally unbounded regions, we always see a plus infinity or a minus infinity, so it's just obvious that it's improper. We see that infinity symbol. But when we are dealing with a vertically unbounded region, not obvious. So this integral, a to b, in Calc 1, you never really did an in-depth analysis, even though it was probably mentioned, that this is only a definite integral if this function f is continuous all the way on that interval, a to b. This function is not continuous at a, right? It's discontinuous at a. That's why this is not a definite integral. So you can look at an integral and you see these numeric limits of integration and you're like, it's a definite integral. Not necessarily. It's a definite integral if the function is continuous on the closed interval AB. But you can see in this picture, we're not defined at A. So that means it's not a definite integral. So the way we're going to approach this conceptually is the same as the other one. We're going to integrate over here and create a definite integral. So I'm going to pick a c value that's somewhere between a and b. And the integral from c to b is definite. That's a definite integral, c to b. And then we're going to do the same thing we did in the last with the horizontal ones. We're going to then take the limit. But now the limit is as c, not going to infinity. C is going to approach a from the right-hand side in this case. So we're going to be dealing with one-sided limits. So we have to make sure we understand that we're approaching a from the right. If the asymptote is, if we're on the other side of the asymptote, so here we have integral from a to b, appears to be a definite integral, but then we realize, oh shoot, the function's not defined at b, this is an improper integral. The first word we write is limit. We're going to create the definite integral from a to c, and then we're going to let c approach b from the left-hand side. We're approaching that asymptote from the left. And if we have a double tail, like that, we just break it into two integrals and drag on twice as much work. We have to figure out the area coming in from the left of the asymptote, figure out the area coming in from the right. So we have two separate integrals, and we have to add them. All right, so let's try one. Or more. Let's do it. We got it. We have to. We've come this far. Okay, so reminder, this is 1 over x squared. You can see that 1 over x squared approaches the x-axis very quickly. And we did this, right, already. So the integral from 1 to infinity, we already did. The integral from 1 to infinity we found was the integer 1. All right, so 1 to infinity we've already done. Now we're going to consider integrating from 0 to 1. So we're just going to look at this vertical tail. And can you see that as you increase the power on x in the denominator, it's going to squeeze in on x, but it's going to peel away from y? If you looked at 1 over x to the 4th, it would be tighter to x and looser on y if you get further away from the y-axis, if you were to look at graphs of them. Pretty obvious that this should be infinite up here because it's nowhere close to getting tight on y. It is approaching the y-axis though. If you go far enough up, it's going to become indistinguishable eventually, but it's going to be very, very slow. So our hunch should be that this is infinite. That's our hunch. So we already know that the horizontal tail is finite. We did that already. Now let's do this one. So here, you look at it, that's improper. It's not obvious though, right? You don't see infinity. You need to start looking at the interval and recognize that, oh gosh, it's not definite because 0 causes an asymptote. 0 plugged in gives you division by 0, which is going to create a vertical asymptote. So that's not a definite integral, even though it really looks like it. So as soon as we know that it's improper, the next word we write down is limit. Bless you. And so what we want to do here is imagine creating this B. We're going to find the area of this. Actually, they use C for this one. They use C, not B. I'll use the same letter they use.
So 0, 0, so B.
And we're going to approach 0 from the right. So this is going to be the limit as C approaches 0 from the right. We're coming into 0 from the right. We always have to stay in our interval. And this will be the integral of c to 1, x to the negative 2 dx. So everyone see how we partition this? Pick an arbitrary point there, and if we integrate from c to 1, this is now a definite integral. But then we're going to let c approach 0 from the right. Yeah?
Could you integrate with respects to y and have that work?
You could convert everything over to functions of, instead of functions of x, functions of y. You could. Yep.
Yeah. Okay.
It might get a lot messier. It might be easier. There's no way to know if it's worth doing. But doing it without converting is not too hard. So There's not a big advantage. Usually we'll convert variables if we can't do an integral. Then we'll do some sort of modification of the variable. But because we'll be able to integrate this just fine, there's not a big advantage to that, but you could. You could be dealing with functions of y instead of x, for sure.
And then you just have the limits be the infinity
And in this case, 0.
and, yeah.
Yeah. Yeah, you could definitely do that. Although the one drag with that one would be, actually, now I'm thinking about it more carefully, is that you would have the y going to infinity for that upper tail part, but you actually also are going to have this lower, because this is all the way down to the x-axis, that would also be infinite. So you'd actually have to be doing 2 improper integrals if you did switch it. So that would be a little more work in this case. So when we integrate this one is not so hard to integrate. Add 1, divide by the new exponent, so we get negative 1 over x from c to 1. And if we plug in our limits of integration, we have negative 1 minus a minus 1 over c, 1/7. 1 over c. And what's that limit? Oh, that was good. No one fell into the trap? Somebody must have thought the trap. So if you don't put that little limit subscript there, it's very tempting because of all the ones we've done so far is to say that this limit is 0. But c is not going to infinity. C is going to 0. So the limit is not negative 1. That can be a mistake people make. So let's think about 1 over c. So it's really important that we're dealing with one-sided limits here. Because if we were approaching 0 from the other side, we'd be dealing with negative numbers, and this would be a negative number. Right, but what we can say is that if we're approaching 0 from the right, the c values are always positive. So this number right here is always bigger than 0. Right? It's always bigger than 0. And as the denominator gets closer and closer to 0, that means the fractions have to be getting bigger and bigger in magnitude. But they're always positive. So this is going to positive infinity. And if you subtract 1, still going to positive infinity. So you don't have to write the plus. So that is going to go to positive infinity. Everyone see that limit? Yep. So the denominator is getting closer and closer to 0 through positive numbers. Like if this was a two-sided limit, you could not necessarily write that. Well, let me ask you. Let's ask that question. So what if this was a two-sided limit? So c goes to 0 of, let's just forget about the negative 1. What about that? Can you write, what is the only thing you could write right here?
Does not exist.
DNE. It's all you could write. You cannot write anything else because when c is coming through positive values, so if we were approaching 0 from the right, this would be positive infinity. But if we approach this from the left, so if we come into 0 from the left through negative values, this is going to be negative infinity. Right? This one, the numbers are always negative. This number is still going to 0, but it's always negative, so the fraction's always negative. And as we approach c as c goes to 0 and we approach from the left, these are always negative, but they're going to get bigger in magnitude. Negative 0.1, negative 0.01, negative 0.001, negative 0.000001. So the magnitudes are going to be growing, but they're always negative. Here, always positive. Here, you don't know. It's positive or negative. The only way a two-sided limit can exist is if both one-sided limits exist and are the same. So that's a good example of what we were talking about earlier. So here, all we can write is DNE. If you look at a picture of the graph, If we look at the graph of 1 divided by x, right, that graph looks like this. So as we come in from the right, it's going to positive infinity, but when we come in from the left, it's going to negative infinity. So the two-sided limit, all we can say is D and E does not exist.
We can only give it a definite answer if we're doing one or the other.
Yeah, exactly. Correct. Okay, so as we're starting to see some patterns here. If we've got our curve in quadrant 1, as it gets tighter on x, it gets looser on y. And now we are going to see that the opposite is also true. That if we get tighter on y, we get looser on x. So now, power on x, let's put a power on the x that's smaller than 1. So we've seen that the power on x getting bigger in the denominator. We have convergence down in the horizontal tail, but we have divergence up on the top, on the left tail, the vertical tail. So now look here. When we go x to the 1/4 in the bottom, you can see how it pulls away from the x-axis. So that's telling us that that horizontal tail is going to be infinite. But it gets tighter on the y-axis. And so you can just look at the graph and suppose, oh yeah, it looks like that's probably going to converge because the function and the y-axis are becoming indistinguishable from each other. So let's check. So let's do both. We'll do the vertical tail and the horizontal tail. You guys do it. Do this one first. Do the horizontal tail first because that's the one that we've had experience doing pretty quickly. So you should be able to do that one pretty quickly. So do the horizontal tail first. But in your mind, the math should just confirm what you should have very strong intuition going into doing the math. And if you look at that graph, you should be saying to yourself, oh, this is going to be infinite. But that's what the math is for, to prove that that is infinite. Any snags on that first one showing that that horizontal area is infinite? Right?
I'm so surprised.
Wow, perfect. I mean, that's good because we're just learning it today for the first time. So shocking. So I'll rewrite the... No offense meant. Really. So that's the first one. We see it's so obvious that it's improper because we have that infinity symbol jumping out at us. And we do our typical power rule stuff. We add 1 to the exponent, getting 3/4. We divide by 3/4, which means multiply by 4/3. And then this limit is as b goes to infinity of b to the 3/4 minus 1 to the 3/4, which is 1. And here, when you look at that 3/4 power, you should be seeing the bird wing. Anytime we've got that proper fraction as the exponent, this is going to infinity. It's going to infinity slow, but it's still going to infinity, so this limit is infinity. Any questions on that horizontal tail evaluation? Is that okie dokie? For the vertical tail, not obvious that it's improper. Right, we really need to know what's going on. We need to know that this is causing division by 0. So we have to have a sense that this is not definite. It's not a definite integral because the function's not continuous on the closed interval. So here, we'll pick a c, and we're going to go to 0 from what side? From the right. So when you're thinking about this interval, 0 to 1, we always want to stay within this interval. So if we pick a c value in here, we're finding this area as our definite integral, but then c is coming to 0 from the right-hand side. Because all the values are to the right of 0, so we're approaching 0 from the right. So super important that that's a one-sided limit. Then stuff looks a lot like it did on the other problem, right? We still have this whole x to the negative 1/4. So that part should look really similar. Bless you. So here, we have the same antiderivative, x to the 3/4 divided by 3/4. Our limits are different, though. And we can factor out the 4/3 if we so desire. And then we're going to have limit. 1 to the 3/4 is 1. C to the 3/4. And c is going to go to 0 from the right. And when we look inside this limit problem, we have 1 minus c to the 3/4. C is going to 0, not infinity. 0 to the 3/4, 0. So this whole limit piece in here is going to 1, so our answer is 4/3. So the vertical tail is finite. It's an unbounded region that has finite area. Versus the horizontal is an unbounded region with infinite area. So even though it doesn't look like it, there's still a little tiny gap here all the way up to the top forever. So both of these areas are unbounded. That one is infinite. That one is finite. And so we're always going to have this sort of tilting thing. As we get closer to the y-axis, we get further from the x-axis. As we get closer to the x-axis, we get further from the y-axis.
And do we not have to check approaching 0 from the left also? Or
That's not part of this region, right? This region ends at 0.
Okay, yeah.
So the function is not defined to the left of 0. At this function, we're only looking for positive x's. So if we have a vertical tail and we do have function defined on both sides, then we have to break it into two pieces. All right. Okay. Let's do one more of these. So the function is graphed. This is another one I'd give you the graph. A lot of these you don't even actually really need to know what the graph looks like. As long as you can pinpoint which endpoint gives you the asymptote. Like when we look here, The integral, again, you look at it and it doesn't immediately strike you as improper. But if you plug in the -3 there, you realize, oh, the -3 is giving division by 0. That means that we have to use an improper integral technique. It helps to have a picture, but you don't really need it. When you look at this interval from -3 over to +1, it instantly becomes obvious that you're coming to -3 from the right. Whereas if it was the right endpoint that was bad, if it caused division by 0, you'd be coming to the right endpoint from the left-hand side. So it all depends on which endpoint is your bad endpoint. If it's this one, you're coming in from that side, from the right. If it's this one, you're coming in from the left. A picture always helps, though. So first thing we write down whenever we have an improper integral is limit. We're going to approach -3 from the right-hand side. So from c to 1, that's the gray area. So c to 1, this is a definite integral. We're finding that area, and we're finding it as a function of c. Does that piece make sense to everyone? That we're finding a function that measures that definite integral, but that function can then be evaluated with the limit as c goes to whatever our endpoint is. Any drama in your head? No drama in your head. That's great. We can't always say that in calculus too. Okay. And how should we rewrite this integrand so that we can integrate it? What are we going to do with that function?
Turn it into a negative exponent.
Yeah, we're going to take that quantity, we're going to move it up to the numerator, cause the exponent to become a negative value, then we can use the power rule. Yeah, 100%. So the way that our evaluation will work is by doing that. Now we can use a combination of the power rule with reverse chain rule. Exactly. Absolutely. So this is pretty straightforward. We're going to add 1 to the exponent and get a third. We're going to divide by a third, which means multiply by 3. And then what's the RCR part?
Divide by 2.
Divide by 2. Yeah, exactly. So we'll divide by 2. And the limits of integration are c to 1. So we have that. The 3/2 can come out to the front. And then we're going to have limit of, first we plug in the 1, and we'll have 6 plus 2, so we'll have 8 to the 1/3. 8 to the 1/3 is 2 minus, we can't simplify this thing, 2c plus 6 to the 1/3 power. So we're going to take the limit of all of that as c goes to whatever it's going to, -3 from the right. So that's where we're at. Now, before we actually do the evaluation, let's play with our intuition for a second. So we've seen that these vertical tails so far are finite when the power on x is smaller than 1 in the denominator. When the power on x was bigger than 1, the horizontal tail was finite. But the vertical tail is finite when the power on x is smaller than 1. The vertical one is infinite if the power on x is bigger than 1 in the denominator. Is the power on x bigger or smaller than 1? Smaller, right? 2/3 is smaller than 1. So our hunch is that this is going to be finite vertically, and this is going to be infinite horizontally. So that's what our intuition is telling us. So then we start to evaluate. The nice thing here is that when we approach -3, We just plug it in and see what happens, and if we get a number, then we're good to go. We don't have to do any weird analysis. When we plug in -3 right there, this part all becomes, on the right, what is that? It all becomes 0. -3 times 2 is -6, so this is all 0. So this is our limit. And that is the area of our vertical tail. Integer. So evaluating limits becomes vital. Vital. Okay. Let's look at this crazy looking thing, unless someone has a question on the other one. Another function that you would never be expected to graph. So the function is looking all weird. Vertical asymptote at x equals 0. All right, you guys try this one. At least write down the setup. We'll finish it off on Thursday probably. So see if you can set it up properly to find that blue, to find the area of that whole region from 0 to natural log of 3. Yeah.
I have a stupid question.
Sure.
So, we're doing so we're going to replace this.
Well, sometimes it could be, it depends on if it's the right or the left endpoint.
Okay.
If it's the left endpoint, then the bottom becomes C. If it's the right endpoint, then the top becomes C.
Okay.
Yeah.
Awesome.
Yeah. So it just depends on whether you're to the left or the right of the asymptote.
Okay. Thank you.
Stop me if there is a piece as you're starting to write it down that you're not sure of.
Yeah, obviously that's just equal to that right there.
Right.
I kind of want to do the same thing.
Yeah, you
but
can't
then-
do that here.
Yeah, so maybe I'll just.
Here you want to just leave the integrand as it is.
Okay.
You know, when you have a power on x, that's when you bring it up to the numerator and make it negative. But if you have something more complicated, you generally don't want to move it around. You want to keep the positive exponents. Do you see the technique of integration that we're going to use? U sub, right? If you let u be that quantity in parentheses, its derivative is the numerator, right? Yeah. And everybody's clear that it's the lower, the left endpoint, that's the bad one. And when you plug in 0, e to the 0 is 1, 1 minus 1 is 0, so it's that lower limit or the left endpoint that's the bad one. So you're going to approach that from the right-hand side. Is there any questions on writing down that integral with those limits? Does that make sense? Clicking. Clicking's a good thing. Unless it's coming from your end.
What did I miss? Am I on the right track?
You are. Oh yeah, you're totally on the right track. U is equal to that. Yeah, you're on the right track. Let's finish it off. So U substitution, e to the x minus 1, so du is going to be the numerator. So yeah, the integral should turn into something pretty comfortable. And now we don't know the u limits, and let's not find them. So, and that's right where you were at, right, Tom? U to the 2/3 on the bottom. So then you move it up to the top. And once we move it up to the top, then we can use the power rule. So we have u to the negative 2/3. We're going to add 1 to that exponent. So we get u to the 1/3 divided by 1/3. And when we do our back substitution, we'll have 3 times e to the x minus 1 all raised to the 1/3 power from c to natural log of 3. All right, I'll stop there so we don't rush through the last evaluation step. Is there any questions up to that moment before we plug in our limits of integration? Everyone see how we do the evaluation to get to the u to the 1/3? You see it?
Yeah. I added it.
It's never the calculus, it's always the arithmetic.
It is.
All right, well, we're turning our clocks in less than a week. It's not going to get dark till 7. Isn't that awesome?
Love that.
That's going to be such a good day of the year.
You have the answer.
Stays light later. Gotta love that. What was that?
Do you have the answer available?
No, but we can find it.
Yeah, because in him we got
Something different?
not something different.
Okay, yeah,
we got something. We're trying
Yeah.
to make sure we did everything. Right.
Yeah. I'll put a mark here just so I know that we're going to start from here on.
Because we have everything the same.
Let's see. So if you plug in natural log of 3, you get
problems in surface area.
Program my copy right now.
It probably is.
Did you get 3 times the cube root of 2?
Yeah.
You would have to take the limit of that expression at infinity.
I'm getting obliterated, bro. I'm kind of people who not the grass or go outside.
That sounds like a fun crazy because we kept getting cubed with the same duos in our bosses. Because we kept winning and they kept winning the game, but we were winning enough to.
Thank you.
Yeah, have a good one. I was up, I went up to a hut of Yeah, it was great. Yeah, we skied up.
Like every time they got a
Eagle.
they just fucking
Super good, actually. Where did you go?
Yeah, it's
Oh! Yeah, like not sisters or,
I don't think it was sisters.
yeah, it's so weird. It was one of the big ones.
It's like a rotating disc.
Yeah, sisters is down there. I haven't been to those ones. This one was, it was cool. So they're south of Eagle, and we could see the ruined elves. We could see Capitol Peak.
It just does all the things.
It's a fun place. It's super remote back there.
You should ask the best
Yeah.
on the exam.
It was it was 6 miles.
Bring
to get
clay,
in.
and that
Machine
calculator.
race cars that, we ended up buying
Technically,
like
I mean, it only
RCR
gives you the
off-roaders
literal
because he's like, well, there's no race
No,
car
what is
tracks
it?
around here, but there's
What
hundreds
is
of
the
miles
answer?
of
Just tell me
off-road.
the answer, yeah, that's not gonna be
Yeah, we saw a lot of people that were doing crazy things up there.
Oh, it's one of those like four.
I think it's fixed as well, but that one day you said like if I saw the identity, I could just plug it in.
Yes.
I'm still doing something wrong though, because eventually I would end up losing it.
So you're subtracting the negative.
Imagine
So
up
he
with
had
that.
his racing sim was all called livery.
So negative infinity
And
is
his
0.
Razor was all like
That's
color
going to be
colors.
percent and that. So like A.
So what am I talking about?
Is he doing flat race?
Oh, first thing, this should be A, not negative infinity. Like as soon as you.
Yeah, convert, yeah.
Yeah, so my guess is that that might have something to do with
Yeah, it
it.
is.
So
He
let's
just
get
watched
those
the
in
real
first,
there's no
and
race
then that
cars
should
around,
be
but
a
That
B.
wheel, I just
last 5 minutes to 100 miles.
that constant speed.
So we always want to, we want to have limit as part of the problem until the very, so we should be doing all the upper minus lower stuff with an A or a B.
To make it a function.
To make it a function, exactly.
Like it's so simple.
Okay,
You're like, well,
so-
of course. It's-
And my guess is that you lost the subtraction somehow in that process, so this is going to be 10.5 minus, that's out in front, so.
Which one is it integrating? Is it finding the volume of the model?
No, it's
So.
But, well, yeah, and then I just put negative.
Yeah,
Which, yeah, is the correct notation, I
Yeah, it's
guess.
not correct notation, but that's okay.
over it. And as the wheel rotates, it sums up. Like, so the further it moves along, the
So,
which is like the higher the function is at that point.
this part is going to
Most well known.
negative infinity, so that's negative pi over 2, so this should be minus pi over 2, which is plus pi over 2.
Okay. And why is that even, sorry, because there's a negative here,
So,
because it's approaching pi over 2.
yeah, let me think of this time. I was getting, so this A is going
Like you just, you couldn't work out.
yeah, this is going to negative pi over 2, and you have the subtraction in the front.
Okay.
So you have the subtraction, and then this is going to negative pi over 2, so that should be going to positive pi over 4.
Okay,
Yeah, that's the error right there.
so then I ended up.
This one is correct, though,
Oh, okay.
because this is going to positive pi over 2, and then half of positive pi over 2 is pi over 4.
Okay, yeah, why did I think that? So I put negative infinity over 2.
And so when you're looking at that inverse tangent function, it's going to negative pi over 2. So it's doing this. So negative pi over 2. And you've already got a subtraction in front.
I see what you're
So your
saying.
subtraction is in front.
Because yeah, as we approach negative infinity, it's going to negative pi over 2.
Yeah, so we're going down the x-axis towards negative infinity, and the y values are going to negative pi over 2.
Okay, yeah, that would be enough to get to fix it, because then I get.
Yeah, then you get pi over 2.
Yeah,
Then you get pi over 2, which is
yeah, the answer.
which is the answer.
Yeah, thank
That
you.
is the answer.
It's like, when's the test? Is it Thursday next week or Tuesday?
Oh, we forgot to talk about that.
Thursday.
It should.
Thursday sounds right.
In fact, you could literally just.
Yeah, the
erase
test.
that too.
Oh my God, the test is the day before spring break.
Oh boy.
I can't believe spring break's that close to us. How is that possible?
Better than right after.
Wait, is spring break really starts at the end of next week?
Yeah.
Wait, what?
Wow.
Oh yeah, isn't that crazy?
Wow, that's crazy. So we have 3 more class periods, and then it's spring break. We have Thursday, and then Monday, Tuesday, and then it's or Tuesday, Thursday, and then it's spring break.
Who cares about spring break? 3 classes till the test, is that? what's
Yo, that's more important to you. The test is a week from Thursday. Wow. I've been a little delirious the last week with this head
Everyone's
cold.
blowing my mind today.
Yeah, I know. My mind's melting.
Today's a rainy day, it's feeling weird.
I know, and it's raining outside. What is up with this? It's winter.
I know. I'm seeing ladybugs everywhere.
Yeah, I've seen
I know. Yeah, we got honeybees in our front yard.
And I just want snow. Hopefully we get a good snow.
go snowboarding.
I don't know. My kids are off rock climbing in shorts and t-shirts. I'm like, really?
I haven't seen a rock in days.
Because of the fog?
Unless I was integrating the volume of a rock.
Find the volume of this rock.
Like calculus 3 stuff.
The weather up there has been pretty warm too, though, right?
I haven't been up there.
Oh, where have you been?
Here.
Have you been sleeping down here?
Yeah, it's a bit easier to get places on time.
Yeah.
Saves like 4 hours of driving.
Yeah,
So
yeah,
that
yeah.
more calculus.
Have you found some places where you can be crafty?
Not as good as Estes. It's harder.
Yeah,
It's a lot harder.
Is there like a Walmart type thing?
Yeah, they don't do the overnight parking stuff anymore. Like they'll
That's what
let
I
you,
heard.
like it's not allowed, but you won't get like towed in one day.
Yeah.
But you don't want to be there for like a week. So.
Yeah, right, for sure. Yeah, then they'll pay more attention. So you're going into neighborhoods then, or?
Usually, I don't like to park by people's houses.
Yeah.
Because I wouldn't like that if someone did that to my house. But there are neighborhoods that are under construction, like dead end roads at the very end.
Yeah.
Or like no one's built in the land yet, so you can park in front of
Yeah,
that. So
yeah.
usually there. Nobody asks questions about you all truck in a neighborhood.
Right, exactly. Yeah, because you're a little more conspicuous. I don't think I've seen a picture of the outside. Do you have a picture of the outside of your rig?
I don't know. It's not that interesting. It doesn't say U-Haul anymore. It's just like a blank
box
white
van,
truck. Yeah.
not a box fan, but yeah.
Unfortunately, when they sell the trucks to you, they cover it in vinyl.
And down near Stanley Lake, is there options down there?
Stanley Lake?
Yeah.
I'm not sure what it is.
If you go down Sheridan, so if you go down Sheridan and take a right on like Independence Road, I think it's called, it takes you over to Stanley Lake, which I wonder if there's some subtle areas over there that could be easy to use.
There's the other side. Those straps are gone now.
Mhm.
Just it's kind of ugly, but just like
Yeah. That's what we need. And then there's that bizarre looking thing.
definitely gives it away.
Was that original, or did you?
I installed
You
that.
installed it,
so.
yeah. Yeah, it's invented.
I couldn't put it on the top because then it would suck the smoke in from.
Oh, yeah.
chimney.
Yeah,
You
yeah,
just-
yeah, yeah, yeah,
then you
right.
just die.
Yeah, that's not the move. Yeah, I wonder if near Stanley Lake, there's a disc golf course down that way called Johnny Roberts, and there's a little park there. I wonder if that would be kind of a inconspicuous area. Johnny Roberts.
Oh, over there, okay.
But at Stanley Lake, I would think there would be some maneuverability there.
It could be. I don't know about that lake. I've heard of it, but a lot of lakes have like some kind of park that has a park ranger nearby.
Well, there's different, that lake is huge, and there is one side where there's a boat ramp and there's a little more,
Yeah.
kind of official stuff, but there's definitely some areas around that lake that seem, maybe you're across the street from some housing, but you're not like right in front of someone's house.
So I see on the map here, yeah.
I had a couple
Question, Richard?
questions. Yes, so, that's what I got. I think I got the same.
Yeah, that's it, perfect.
Cool.
You got that on your own?
Yeah, I got lost here.
Good.
Because I always forget for the
Evaluating the limit.
variables,
Uh-huh.
yeah, to put in 0 for the limit
Yep.
instead of just what the limit is around that area.
Gotcha, yeah.
Yeah.
Yeah, so you're
And-
plugging in that 0 and
Yeah.
then evaluating e to the 0.
Yeah. And then,
Oh, that looks great.
when I was studying or working on the homework for the voodoo
Mm-hmm.
stuff, I was trying to find a way to quickly figure out what to put and where,
Yes.
and I came across this acronym.
Yeah, the Liate.
Yeah, is that viable?
That's
'Cause
totally
I know
viable.
we didn't talk about it.
Yeah, for me, that never worked for me, so I don't,
Okay.
I don't like trying to teach things that don't work for me.
Because I
Um,
saw it and I was like, well, we didn't mention it, so it's probably not.
It's generally, when you have calculus taught by an engineer, a lot of times that's what they'll use, because that's
okay.
more prescriptive. I try to approach it a little more conceptually, and And the general rule of thumb that I try to emphasize is that we want the biggest piece that we can integrate. So the biggest piece of the integrand up here, so whatever this stuff is up here, the biggest piece that we can integrate easily, we want to drop in there.
Okay.
So my focus is always on the DV, whereas that focus is a little bit more on the U. And it's like, okay, if there's a log, or if there's an integral, or an exponential, or whatever, a trig function. So I tend to focus more over here and just try to grab the biggest piece that I know I can integrate. Because usually we're dealing with things that, there's usually only two functions. So there's not a lot of choice. So if we look at the two functions that are in there and one of them's easily integrable, that's 90% of the time that's going to work.
Okay.
But that's not a bad, scaffolding, triage way to go through. I don't even remember what all the letters stand for. L is
Logarithms, inverse.
Oh, inverse was I.
Inverse tangents,
And then A was
algebra, trig,
algebra,
and then
trig,
exponential.
and then exponential. Okay.
Yeah. That kind of makes sense.
Yeah. I don't think it's bad to have a strategy for sure.
I'm doing this one,
Mhm.
the worksheet, and so I'm ending up here. I can add these, right? These exponents together.
Correct.
So then I
Oh,
would.
you multiply them.
Oh, yeah.
Multiply
Multiply
them.
across.
Yeah,
Right.
power to power, you multiply.
Yeah, I
Sorry.
think I'm getting tired.
I jumped to add before.
No,
I
that's
thought you were
okay.
talking between the numerator and the denominator, you add or subtract.
Okay.
Between
yeah.
numerator and denominator.
So, yeah,
But
then
power
I-
to power, you add.
5, then I get secant to the fifth.
Right.
Okay. Alright. And then 2 of these will cancel?
Two of those will cancel. Mhm. Mhm. And that's a secant in the denominator, so if you move it to the numerator, it becomes
To the negative third? Is that what you mean?
you can write secant to the negative 3, but what is the reciprocal of secant?
The reciprocal of secant? Negative secant? The
Reciprocal, yeah. What's
Oh,
the
no.
what's the reciprocal
To the negative third? We're saying now secant to the third.
So if you have, so let's forget about the power for a second. If we have 1 over secant, what is that equal to?
Oh, cosine.
Cosine, right. So if you have secant cubed down in the denominator.
Oh, I have cosine cubed.
Cosine cubed up top.
Okay.
Yeah,
Thank you.
yeah. No, that's, the terminology can,
And then for my other question, I was doing this for a lot of the problems
Mhm.
with the infinites. Is
that's
this
totally fine.
Fine?
Yeah, it's
Okay.
fine, yeah.
Yeah.
There's some people like Charles would probably not like you doing that.
Yeah, because I know like the variables are important for when we're trying to do other stuff, when we have to change things and everything. But
This is a really good way to conceptualize
yeah,
what's
that's
happening.
Yeah, because I was like, well, I could just look at it and be like, oh, it's going to be infinite.
Yeah, exactly,
Yeah.
exactly. Yeah, I'm fine with that. I
Yeah.
probably won't write it that way on the board just because there's some people that would take offense.
Yeah.
Because it's not technically proper notation, but I think it's fine.
Okay.
And I think if our notation reflects an understanding of what's going on, I think it's fine to use it.
And then I think I started one differently earlier. Let me see if I can find it. Maybe.
It's so cool these days to be able to just go through
Yeah.
notes like this.
It's nice when the pages load. If you close it and then reopen it,
It lag.
yeah, well, it just does like, oh, I need to refresh. It's like, why?
Yeah, yeah.
This one, so I
Mhm.
just broke it up instantly and saw it was just
So now
natural law.
you can't have infinity in both these places.
Okay.
So that you definitely want an A up in the,
Okay. So
So-
that one you would have to.
yeah, that you definitely want A there.
Got it.
So we can't evaluate the integral until it's a definite integral. And so it's not a definite integral until we get rid of that.
Got it.
And so then this is going to be, oh, and
Yeah.
you did put an A in there?
Yeah,
Oh,
yeah,
yeah, you went
thank
back. So one thing that's missing, you want to be careful, you still have limit out in front.
Mhm.
So make sure you know, on the test especially, you limit still. Yeah. Yeah, and that's all good.
But this is fine to do it this way, to like just break.
That's all
my
fine there.
integrals.
Yep,
Yeah, 'cause
that's
I did that.
Yeah, and it's a notational thing, like in math, it's, this is definitely preferred.
Yeah.
But all the time we do it as just shortcut, we'll do that.
And it was
Just to save space.
The other one was,
But technically,
I remember which one it was, but I think I didn't write it down. It was, see if I can find it, not that one. This one. So the way I was looking at this one was I was going to do it this way, which was just going to be but I know you did U sub.
No, this is how we did it. That's how we did it.
Oh, okay.
That is how we did it.
Okay.
Yep, yeah.
I think
I mean,
it was
the-
a similar one where we did U sub.
Yeah, so if,
I forget which one it was.
there was the one with like the e to the x plus 1 for you.
Maybe, yeah. That
This one for sure you do it that way. Oh, that
Oh,
one.
that one.
E to the x
Yeah.
minus 1. That one you'd have to do
Yeah,
U
because
sub.
that one I thought, oh, well, I could just do the same thing, right? And then I looked at it and I was like, oh, I could just distribute this. And I was like, wait, maybe I can't.
Yeah, you can't.
'Cause that
There's,
looked
yeah, there's,
messy.
yeah, there's no distribution here. This one you would
Yeah,
have to
because
do
I was
U
like,
sub.
wait, you can't do that because
Yeah, there's no way to combine
Yeah.
those two. Yeah. So
And
you
then I was
can't
like,
distribute
okay.
the 2/3 over to there and then
Mhm.
combine.
Yeah.
Yeah,
Yeah.
that one you'd
Okay.
have to use U sub.
In a U sub, my 1 would become a U also? Or it
Mm,
becomes,
this is 1 minus U squared. Oh, well, when you integrate.
yeah,
When you
okay,
integrate,
sorry.
yes. When you integrate the 1, it becomes a U.
Okay.
That's right.
Thank
Yeah,
you, yeah.
Yeah.
And then my last question was, so the concept of the infinite
Gabriel sign?
limit. Yeah, well,
Or-
that one I was just like, well, I mean, you could just flip it inside out and there you go.
Painted.
It's painted. But
Yeah.
my other question is, so if I'm remembering Calc 1 correctly,
Mhm.
our integral is just an infinite number of rectangles on the inside, right, to find the area. So if we're doing the limit of a limit, how does that work?
Well,
Conceptually.
that's a great question. So you have nested limits, because when we are thinking about, if we were thinking about just a regular integral from, just say 1 to 2 of this function, you are correct. This definite integral has a limit built into it, right? We took the limit of the Riemann sums as n goes to infinity, I equals 1 to n. This limit becomes this integral, and then we are just doing a limit of a limit, though. You're right. It is a limit of a limit. There are nested limits. So it's just that we evaluate this limit first, and then if this happens to be, a bad point causes division by 0, then we are doing a limit of a limit, which is fine.
Okay.
It's just like a composition. When we have f of g of x, first we calculate g of x, and then we plug it into f. So it's that same idea. The definite integral is coming from this limit, but then we're going to take the limit of that, so it's a limit of a limit. But that's okay. We evaluate this one first on the inside. That one's kind of hidden,
Yeah.
because that one becomes this integral. So that one's, we don't ever write this one back down, except in Calc 1, where you
Yeah.
have to do those left and right
The
endpoints.
sigma notation.
The sigma notation. Yeah. But that is true, though. It is a limit of
Okay. And then if we had a problem that was like those, the circular integrals where it's like cosine of e
Yes.
to the x.
Yeah.
And we had
So
to do
the
something
integration
like
by parts
this.
with a twist.
Yeah,
Mhm.
we use something like that for this?
We,
Or would
I
it
mean,
be
it's
like-
possible to end up with an integrand that we would need, integration by parts with a twist. There's enough going on here that we're not gonna, the homework, I don't think they combine those anywhere.
But it would be
It's possible.
to do it, okay.
It's possible.
It would just be following the steps up there and just adding the limits. in
Yeah,
those places.
except we'd have limits of integration instead of, indefinite integrals.
Yeah.
Yeah.
Okay.
But it is possible.
Okay.
We hope not to see it, but. I can't remember, I don't think the homework has any in there. Sometimes I forget though, but I don't think it does. Yeah, that would be mean. Integration by parts with a twist on top of an improper integral.
I don't know, I mean, if you know your integration by parts, I don't think it would be that much.
Yeah, it's not that
difficult. You're just adding another boundary.
Another element of Calc 2
Yeah.
integration techniques. How's the worksheet going?
I'm gonna start that this week. I've just
Okay.
been focusing on
Yeah, I
physics.
totally spaced out. I meant to
Yeah,
mention
I
it.
forgot about it too, and I was like, oh wait, yeah, there's worksheets too. for
Yeah,
this.
it's due Thursday night at midnight.
Yeah. I was
Yeah,
like, oh yeah, that's this week.
Yeah, I can't, I'm shocked.
Yeah, because I was.
This semester feels just, I always have this feeling that the semester picks up, but
Yeah, this semester's.
this
going
semester
by.
just feels like we're flying along.
Yeah, because I was like, when are the exams? Are they before or after spring break? I was like, oh, they're before. And I was like, oh, they're next week.
Yeah, this is week 7. And our semester is 15 weeks.
Is it
So-
15?
Yep. And so week 7 is going to be done, and then next week's week 8. So we're more than halfway done next week. Which I just, doesn't feel right.
Yeah.
Oh, shoot, did I forget to turn off the recorder? We might have an extra long blabbering thing going on here. Oh, I think I did forget to turn it off.